Some extra example problems for section 6.3 and 6.5, because we're talking about word problems here, which usually we need a little more help on. For number one, we're looking at the high temperatures in some city. They have a mean of 23 degrees Celsius. That'll go in the middle. Standard deviation of 4.5. Part A, what's the probability that the high temperature for the day was above 31? So 31 will put me to the right here. So I'm going to mark that off. And I want to know what's above 31. So I want to know to the right. I want to figure out that area. That'll equate to the probability. I need to convert 31 to a z-score. So 31 minus the mean divided by the standard deviation. And if you do that, you're going to get 1.7 repeating. Now remember, be careful, know how to round. We've got to round it to 2 decimals to use our z-score sheet. And that will be 1.78 then for my z-score. So you're going to go to your z-score sheet. It's going to tell you the area left of 1.78, which the area left of that is 0.9625. So we have to do 1 minus that. And that will give me the area to the right, which is 0.0375. So it wants probability, so I leave it as a decimal. I don't convert it. For part B, now I'm looking between two temperatures on this. So again, I still have 23 in the middle. 21 and 27. So I want to know the in-between on these. Well, first thing I've got to do is convert them over to z-scores. So I have to do that with both the 21 and the 27. So 21 minus 23 divided by 4.5. That'll give you a z-score of negative 0.4 repeating. So again, if we round to 2 decimals, that's negative 0.44. If you go to your z-score sheet, the area left of that is 0.33. I still need to figure out the z-score for 27. If I run that, you'll get 0.8 repeating. So again, rounding to 2 decimals, we'd have 0.89. The area left of that on your z-score sheet is 0.8133. Remember, we want the in-between, so we're going to subtract 0.8133 minus 0.33. That will give me the in-between, which is 0.4833. So that's the probability of the temperature being between 21 and 27 degrees. Part C is based off of that. Calculate the number of days in the month in which the high temperature was between 21 and 27, or can be predicted to be that. So I know the probability, 0.4833, it's June, which has 30 days. So if I do 30 times 0.4833, that'll give me about 14.499, which is real close, but If I'm going to round to the nearest day, I would call it 14 days. So I can expect 14 days in June at a high temperature somewhere between 21 and 27. For number 2, the mean weight of a college student is 70 kilograms. Standard deviation of 3. What percentage of students are between 66 and 75? So this is very similar to the 2 temperatures that we just did. So 66 would be below. That should end up with a negative z-score. 75 would be above. That should end up with a positive z-score. And again, I want the in-between. So I first have to convert them over to z-scores. 66 minus the mean divided by the standard deviation. That'll give me a negative 1.3 repeating. So when I round to 2, that'll be negative 1.33. The area left of that is going to be 0.09. 0.0918. A little extra bit on my 9 there. I've got to convert 75 to a z-score. That'll give me 1.6 repeating, so rounded to 2, that's 1.67. The area left of that is going to be 0.9525. So again, we're wanting the in-between, so we would subtract 0.9525 minus 0.0918, and that will give me 0.8607. So about 86% of students are between 66 and 75 kilograms. For part B on this one, let's say McKendree has 2,500 students. I think it's actually less, but we're going to go with that. How many students weigh less than 62.5 kilograms? Okay, so I've got a new X number to deal with, 62.5. I first have to figure out what's the probability of weighing less than 62.5. So I want that area. So I need to convert it over to a z-score. Which will give me a z-score of negative 2.5. Going to my table, the area left of negative 2.5 is 0.0062. So there is a 0.0062 chance that that's a college student weighs less than 62.5 kilograms. But this problem is asking, okay, then out of 2,500 students, how many can I expect? So I have to take my probability and multiply it by 2,500. And that'll give me about 15.5. So I'll round that to the nearest, and we'll say 16 students. Only 16 students out of the 2,500 of McKendree can be expected to weigh less than 62.5 kilograms. For number 3, this one's going to involve at some point the central limit theorem, but the first 2 parts are similar to what we've been doing. So we're looking at the head circumference of a woman. A company makes hats and needs to know how big to make their hats. So the mean is 22.65. The company produces hats so they fit head circumferences between 21 and 25. So 21, 25. What percentage of women can fit into these hats? So I want to know the in-between area. So just like we've been doing, we're going to convert these numbers to z-scores. So 21 minus 22.65 divided by the standard deviation, which is 0.8. That'll give me a z-score on the left of negative 2.06. The area that goes with negative 2.06 to the left is 0.0197. Same thing for the 25, converted to a z-score. You should get a z-score here of about 2.94. And again, we're always rounding to 2 decimals on z-scores. The area left of that is 0.9984. Take big area minus small area, that'll give you the in-between, which on this one is going to be about 0.9787. Now this problem said percentage, so I would just convert it over to a percentage. And if I can get it to write a little better, it would be 97.87%. So I can expect close to 98% of women to be able to fit in these hats if they produce them between those measurements of 21 inches and 25 inches. Part B is a little different. On part B, I'm given the percentages. So let's say instead they say, all right, we want to make the hats fit all women except those with the smallest 2.5% and the largest 2.5% head circumferences. This I'm going to have to work a little different. So I've still got my mean in the middle, 22.65. But there's some cutoff over here, I don't know what that cutoff is, where this area would be, well, I've got to take 2.5, turn that into a decimal, so 2.5 shifted over 2. The area over here would be 0.025. Remember, this is one of these backwards ones where we have to go into the body of the z-score table and find the z-score that has an area of 0.025. If you do that, you should find that the z-score that has an area left of 0.025, the z-score is negative 1.96. Now, what's beneficial here is that the largest 2.5%, that means the area over here would also be 0.025. Since the curve is symmetric, I know that z-score would just have to be the positive 1.96. But now I want to know the X values. I want to know what those question marks are. Remember, we have a different formula if we don't know X. It's X equals mu plus Z times sigma. So I've got to do that for both of these numbers. So for the negative 1.96, the mean, still 22.65. The Z-score is negative 1.96. Sigma was my standard deviation, which was 0.8. So if you run those numbers, you will get the low end X number to be 21.082. And remember, that is the head circumference, that's inches. So on my low end, for part B, it'd be 21.082 inches. For the high end, same formula, except the only thing that's going to change is that Z-score. It's going to go from negative 1.96 to positive 1.96. And if you run those numbers, you get 24.218 inches. So if they're basically going to have the middle 95% of women, that's what they would set their parameters to for their hats. Now for part C, this is going to use the central limit theorem because we're no longer talking about an individual, we're talking about a group. We're talking about 64 women. What's the probability that their mean head circumference is between 22 and 23 inches? Okay, so the actual mean is still 22.65. Now I've got 22 and 23. So 22 is still down here. Oops, that's not what I wanted. 23 is going to be bigger. And I want to know, oops, I did 23 twice. Try that again. 22 over here. But remember, this is a group of 64 women. So my curve actually is much more narrow, but just so I can actually see it, I drew it this way. And I want to know the in-between. So just like we've done on previous parts, in particular we did on part A, we're going to convert these to Z-scores. But my standard deviation changes because, again, when I'm dealing with a group, the standard deviation, actually, let's draw this over here. When I'm dealing with a group, my standard deviation of the sample means is the normal standard deviation divided by the square root of the sample size, n. So for this problem, that's going to be 0.8 divided by the square root of 64, which comes out nice. It is just 0.1. So that is the new standard deviation I'll be using on the calculations, 0.1. So again, I'm converting my X values to Z scores. But now I'm dividing by 0.1 instead of 0.8. That gives me on the left a Z-score of a very small Z-score, negative 6.5. Your table tells you anything, I believe it's negative 3.5 and below, you're just going to say the area is 0.0001 over there. With the 23, again, I'm dividing by that new standard deviation because it's a group, not an individual. That'll give you 3.5 for a Z-score. it says the area left of 3.5 or bigger is, we'll just call 0.9999. If I subtract big minus small, I'll get 0.9998. And it asked a probability, so that's my probability. But now the final question on here, if this probability is high, does it suggest that an order of 64 hats will very likely each fit each of 64 randomly selected women? Why or why not? This, yes, that's a very high probability, almost 100%. But let's think about this. We don't order hats to fit the average head of 64 women. That has nothing to do with what each woman would wear. So calculating this on this problem actually doesn't make sense. So this whole part C really doesn't make sense because the hats have to fit on an individual head, not the average of 64 women's heads.